shard lay out the data in the cluster? What happens when you have dynamic scaling out of the cluster, when you add new machines into your cluster? How does pgshard replicate your data? Then I'm going to talk about the execution logic. What happens when you send a query to the pgshard cluster? How does pgshard route that query? And what happens when there are failures during the routing of the query? This is the talk outline, and I'll have a mini demo at the end. Before we start, I have one slide to put things into context and ask a question. Prior to this conference, how many of you have heard of pgshard? Okay. And how many of you have heard of CitusDB? Okay. And as a quick clarification, CitusDB and pgshard are two separate products that complement each other. pgshard targets the real-time reads and writes use case. In other words, it targets the NoSQL use case. And CitusDB is more applicable when you have big data sets and you want to analyze that data in real time. So you can think of CitusDB as your massively parallel processing engine. And both pgshard and CitusDB shard and replicate your data in much the same way. The table names are the same. The metadata is the same. That's why the two products are compatible with each other. And the reason I had that first slide in there was that we initially started out by saying CitusDB only supports batch data loads. So you have your big data set, you copy your data in. There was no real-time ingest path. And then one of our customers came to us and said, I'd like to insert my data in real time. Do you support that? And we said, we currently don't have that functionality. And they were like, isn't this PostgreSQL? Can't I just route my requests and then do this on my own? And they went ahead and built their own library. I think the first customer is there. And then a second customer came in and asked for the same thing and built the same library. By the third customer, we got the hint. And so we started talking to PostgreSQL users who have big data sets who are looking to scale out their PostgreSQL cluster. When you start running into those limitations, what do you do today? And there were two themes. One theme was doing sharding at the application layer. So this is a lot of effort for the end users or the developers. You need to understand distributed systems and think through what happens when you have failures in your cluster. But this was one of the ways. A second way was you get your data, you denormalize your data, you take a dump of it, and you load it into a NoSQL solution. Of course, you lose a fair bit of functionality when you do that. At the same time, if you don't want to deal with the distributed system complexities, it offers a viable way. So we started talking to more and more PostgreSQL users. We asked them, if you had your top 2-3 wishes out of your ideal scaling PostgreSQL solution, what are they? Of course, if you ask for the top 10 things, that makes up a huge list. But if you ask for the top 2-3 things, we were looking for the what are the most important things to you. And then there were two common answers. One was, I want to dynamically scale out my cluster. When I add in new machines, my cluster should be able to rebalance itself. Similarly, when I have a failure in my cluster, I don't want to manually intervene. I don't want to deal with that stuff. I want the underlying solution to handle that for me. And a second theme was, I want this thing to be simple. I don't want to set up multiple components, or I don't want to configure those components. If I'm using PostgreSQL 9.3, it should just work on Postgres 9.3. If I want JSONB out of 9.4, it should just work with that. So we took all of that in, and we tied it to the architectural decisions. The first decision, dynamic scaling, is what I'm going to talk about next. There, we use the concept of logical shards to make scaling out and failure handling easy. For the simplicity and PostgreSQL compatibility decision, we leveraged PostgreSQL's extension framework. If you look at PostgreSQL's planner and executor, it's built to read in data from disk or memory. So the executor is pull-based. If you're building a distributed database, you want to push out your computation to your machines. So you want a push-based executor. In other words, so your query planner and executor need to be fundamentally different from PostgreSQL, and at the same time, they need to be fully compatible with PostgreSQL. And I will cover that after the next section. So let's start by looking at how to scale out a cluster. First, I'm going to talk about how partitioning has been done in the past, traditional partitioning. So this is your previous era when you have 3 nodes, and you want to partition your data set into those 3 nodes. So a third of your data goes to node 1, a third of your data goes to node 2, and so forth. And then the partitioning dimension here is time. This is clickstream data, so clickstream events. But the data set could be anything, and the partitioning dimension could really be anything. The idea is, let's say you have 12 terabytes of data. You have a table in here that holds 4 terabytes worth of data. Any ideas how this could introduce problems when you want to scale out your cluster? Any guesses? Okay. Well, so let's say you add a new machine into this cluster. And now that you added a new machine, you need to rebalance your cluster. What you're going to do is to transfer large data sets. So you're transferring a terabyte's worth of data from node 1 here. And then you're transferring this data over a gigabit network. So this operation is going to take hours. On top of it, you need to coordinate these transfers from node 1, node 2, and node 3. If there are any failures during these very large data transfers, you need to coordinate restarting those transfer operations. So the operations you're trying to do are very long. And then this is the fundamental problem with dynamic scaling of the cluster. Now that we've seen the dynamic scaling issues, let's also take a look at failures and how failures are handled in traditional partitioning. We now introduce replication into this picture, and then we use exact replicas. So node 4 in here is an exact replica of node 1. Node 5 is an exact replica of node 2, and so forth. Let's see what happens when there is a failure. Let's say node number 1 failed temporarily. In that case, node number 4 will take on node number 1's load. So your cluster's latency and throughput are bottlenecked on this single node in here, node number 4, because 2 and 5 are still taking on traffic. And when you have 6 machines in your cluster, this isn't a big deal. But imagine you had 100 machines. And in that 100 machine cluster, if you have a failure, and it will fail, like you'll have failures, your cluster's throughput will be bottlenecked on that failed node's replica. Also, if this node number 1 doesn't come back up, if you have a permanent failure, you need to re-replicate 4 terabytes of data from node 4 to another place. As a question, any ideas on how to resolve these two issues? Here comes logical sharding. I think Hadoop Distributed File System, HDFS, was the first solution out there to introduce this logical sharding at the system level. So instead of partitioning your data into nodes, you're partitioning your data into smaller shards. And in this case, each shard is 512 megs. And in the diagram, we have the dynamic scaling case. So we introduced a new node, node number 4, and we call the rebalancing function. When we call this function, we'll transfer shard number 4 from node 1, shard number 5 from node 2, and shard number 6 from node 3, in parallel or in serial, depending on your requirements. And then if you have a failure during this transfer operation, these are small operations, so you can easily restart the retransfer of shard number 4. In other words, the rebalancing operations that you want to perform are now much simpler because they're much smaller. The second benefit to logical sharding comes with the replication use case. In this example, pgshard replicated your shards using its default round-robin policy. The idea is no two nodes in this cluster are exact replicas of each other. So there is no exact replicas. And when you have a temporary failure, shard number 1's load in here will go to node number 2. Shard number 6 load in here will go to node number 6, and so forth. And again, not so impressive when you have 6 nodes in the cluster, but imagine you had 100 nodes, and one of them temporarily failed. Then your cluster's throughput will degrade by only 1 or 2%. Also, when you have permanent failures, this data becomes much easier to re-replicate, because you can pull in these shards from the different nodes at will. As a quick checkpoint question, how many of you have known about these problems with traditional sharding prior to this talk? So here's an example pgshard cluster and the data distribution here. Down below, you have your PostgreSQL instances. The worker nodes are exact PostgreSQL instances, so there is nothing there, regular Postgres instances. And then we have a metadata server that holds metadata on shards and shard placements. This is where you create the extension, pgshard extension, and then this is where you create your distributed tables. The metadata server could also be the coordinator node or master node, And what's special about it is that it holds authoritative state on the metadata. So the metadata server is the authority on the metadata. This metadata is typically tiny. It's on the order of megabytes. So it's easy to back up or replicate. And then we keep one row per distributed table, one row per shard, and one row per shard placement. The state changes only when one of three things happens. One, when you create your shards. Two, when you do the rebalancing operations that we've seen previously, so you need to rebalance your cluster. And then three, you have a query that comes into the system, an insertion query. You fail to write to a shard replica. At that point, you need to mark that replica as incomplete. So those are the only three times when the metadata changes. The immediate follow-up question is, what happens when you have the metadata server fail? You could do many things. If you'd like, you can create a PostgreSQL streaming replica of the metadata server. On the cloud, you can use EBS-backed volumes because this metadata is tiny. Or we have one customer here who lost their master node and then reconstructed metadata on the fly from the worker nodes, about 1 million shards or so. To make the metadata example concrete, here's a pSQL command example. This is how the metadata is laid out. On the left-hand side, you have the shard identifiers. So 10,004, 10,005. And each shard, these corresponds to shards on the worker nodes, have a hash token range in place. What that is, for example, you have a query that comes into your PG shard cluster. Say on a table that's partitioned on customer ID, we call PostgreSQL standard hashing functions, get a hash value between -2 billion and +2 billion. Let's say in this example that we got -1.5 billion. You look at this table in here and say, okay, -1.5 billion as the hash value corresponds to this shard, 10,006, and then that's how you route the request. Moving on to worker nodes, there is nothing special about worker nodes. If you log into one of these worker nodes and do a \d, you'll see multiple regular PostgreSQL tables. So one shard placement corresponds to one PostgreSQL table. PG shard automatically extends table names, index names, constraint names on the database for them to be unique. As an example, the shard ID 1001 on the previous example on the master node will correspond to a table name click events underscore 1001 on the worker nodes. So it's all very PostgreSQL-y. And then one thing to keep in mind is when you create your index and constraint definitions, you need to create them before you distribute the table currently. So that wraps up the part about how we lay out the data in PG shard. And let's talk about the logic. The way we're thinking about PG shard is that it strikes a balance between usability and SQL functionality coverage. After talking to PostgreSQL users, we found that everybody wanted a simple solution to get them rolling. And PG shard is just that. You create your extension, and it's there. You then start running SQL commands against your distributed tables. In that sense, you don't need to use special functions, declare special functions to access or query your data. If you think of a lot of the key value stores or document stores out there, they have the concept of distribution baked into their APIs. So if you have a key value store, the data comes in, you hash the key, you route the request. Whereas SQL as a language doesn't have the notion of distribution built into it. And then that's the balance we want to strike here. We want to support a subset of the SQL functionality without requiring any changes to your application layer. And here's a simple example that shows that sets up a PG shard and a distributed table. You call create extension PG shard on your metadata server. You then create a very normal, regular PostgreSQL table. You have your columns here, you have your types, constraint definitions, and your indexes. So there is nothing special about this table just yet. This will become soon a shell table on the master node. And to do that, you call this master create distributed table user-defined function. And this designates in PostgreSQL the customer reuse table as a distributed table. And it also specifies this partition column customer ID is the partition column for this table. Then you call master create worker shards to create your shards and shard replicas. This function connects to remote worker nodes, replays table DDL, index definition, constraint definition DDL commands on the worker nodes, and creates the shards on the worker nodes. The two arguments here, 16 is the number of logical shards you want to have in your cluster. This could be 32, 1,024, or 10,000. And then 2 is the replication factor. So if you have this replication factor set to 1, you'll only have 1 copy of your shards in the cluster. If you have it set to 2, in case any one of the replicas fails, your table's data is still available for insertion and querying. I don't know how many of you are familiar with the internals of PostgreSQL or the internal C APIs that it provides. But one of the wonderful things it gives us is hooks. So we have about a dozen of them, or like 15 of them in PostgreSQL itself. And then these hooks enable you to take control over a command's lifetime at any particular point in time. So they are very granular. And then you can chain these hooks together. So you can get the intercept the planning logic, do your own distributed planning, drop over to another extension, and have that do its own planning logic too. In that sense, they are very flexible. On the other side, there are no strict contracts about what you have to do with hooks or how to override them, so you need to be a bit cautious when you're overriding the planner and executor hooks. For us, the really cool thing is hook APIs give us a very first-class way of hooking into the PostgreSQL system and fully cooperating with PostgreSQL. So it's fully PostgreSQL compatible. And here's an example, or actually here's the overview of our planning phase. An insert query or a select query comes into the cluster. pgshard first checks if it's for a distributed table or for a regular PostgreSQL table. If it's for a regular PostgreSQL table, you fall through to PostgreSQL. And that's one of the neat things. You can have your PostgreSQL database. You can have 100 regular PostgreSQL tables. And let's say you want to query your JSON-B tables. You have big JSON-B tables. So you can create 2 big JSON-B tables and then use them within the same database. Taking a step back, if the query is for a distributed table, then the query would have already been parsed. And then pgshard finds the partition key, applies partition pruning, and then finds the shard or shards involved in the query. Once it finds the shard or shards, pgshard then deparses the query back into the parsed query into a SQL query using the same logic within PostgreSQL, and then sends those queries to the worker nodes. So here's the detailed example of planning in pgshard. An insert into statement comes into pgshard, and then the query gets parsed, and customer use table is a distributed table, so pgshard will take over. It looks into the table schema, the partitioning column, and determines customer ID, and then this value corresponds essentially to the partitioning dimension. It looks up the PostgreSQL hashing function, applies the PostgreSQL hashing function on this value. It then uses PostgreSQL's constraint exclusion machinery. This is what PostgreSQL uses for partition, its own partition pruning logic, to determine the shard or shards that correspond to this hashed value. And then it uses PostgreSQL's deparsing logic, this is in ruleutils.c, to reconstruct a SQL query to send to the worker nodes. In this example, we have this value mapped to shard ID 16. So the final SQL query in here we have is this one, when we deparse this query. And the important thing is, because each work has multiple shard placements, we need to identify which shard we want to write to in here, in this segment.
I'm a little confused because you're talking about the planner, but you don't really have SQL like at that level, right? You have just parse tree.
Yes.
So when you're saying you're creating a new insert, you're really creating a new parse tree that looks like an original insert. Is that right?
Yes. So it's a copy of the parse tree for the insert statement. For the select statement, it will be one or multiple queries. And then we take that copy, and then we take that copied, parsed, and modified tree, and then deparse it back into SQL. Yes, your observation is correct.
Oh, I see. You have to parse it out in the SQL so you can send it to the
yes.
shard. I'm sorry, I missed that.
So we take the parse query and then modify it and then deparse it. We call ruleutils.c. Insert from select. Yes. I'll look that up as soon as we complete, because the select planning is different than the insert planning. And I'll talk about that like in the next couple of slides. And then after, I'll look that up, and then we can look at the query plan. That was the planning logic. And then there is the actual part of the actual execution. You have to be a bit careful here because we're talking about distributed systems. You have parallel requests going on, and you may have failures. We have to think about what safe commutation is on the set of operations that can be performed. So for example, inserts commit with selects, and immutable inserts commit with other immutable inserts. And you can use that property to your benefit if you're willing to relax isolation a bit. We do have full consistency on writes, which means if you write something, you're going to see it when you read it back. There is none of this potential to read from stale data or get back stale results as you have like with some of the document stores out there. PG shard visits replicas in a predictable order. We figured we need to do that in order to enforce constraints properly. And then if any one of the replica writes succeed during the modification operation, we consider the query as successful. So if write to a replica, one of the replicas has failed, the metadata is marked as inactive, and then we take care of that later on. So I'll show that with an example in here too. This is a visual representation of the cluster. You have your insert statement that comes in. The master node looks into this insert statement and says, okay, this is for shard ID number 6. In this case, the replication factor is set to 2, so we need to touch 2 nodes. The connection between the master node and the worker nodes, we have a connection pool, a session-bound connection pool. This is very similar to Postgres FTW. And then in this example, we send the queries to all the replicas. Okay, let's take a look at the example where we have one of those replicas unavailable. We failed to write. So the query comes in, we write to worker node number 1, we fail to write to worker node number 3. The client doesn't know about any of this stuff. To the client, we say we're good. Then we need to do a bit of bookkeeping. So we mark this failed write in here, this particular shard 6 on node 3 as incomplete. So that's the bookkeeping that we do on the master node. To the client, the query is still successful. The developer currently needs to call a user-defined function to repair this particular shard. So there's a bit of manual effort involved there, as in you call this user-defined function in SQL to repair your shard. Single shard selects are very similar to single shard inserts. So you have a query that comes in, we take the where clause, we map it to a particular shard, and then we send the query there, we get back the results and give it back to the client. Single shard selects still have dynamic failover. One difference is, because these are read operations, if you have an intermittent failure on a single shard select, you don't mark the shard replica as inactive. And the use cases here is the common NoSQL use case, the common key value lookups, document store lookups use case. Maybe you have a big JSON-B table that you distributed, and then you're doing short reads and writes on top of that use case, on top of that cluster. So here's an example. You have your select query that comes in that has a where clause. It gets parsed. Master node says, OK, this is for shard number 3. It sends the request to worker node number 1. Let's say this failed. We dynamically fail over. The client doesn't need to know about any of this stuff to the replica, get the results, and give them back to the client. So this all happens automatically behind the covers. One difference here with the insert use case is that in here, we don't mark this particular shard as inactive because this was a read operation. This covers the single shard select use case.
So you always go in that order?
Yes, in a predictable order. So yes, and then because we lay this out in a round-robin fashion, that predictable order changes for each shard. We have many shards, but then the order for shard number 3 is predictable. So we hit worker node number 1 first, and then worker node number 3 second. That was the single shard inserts. If you had a question.
Are all writes gated on master?
Are all writes?
Gated on master?
So all writes flow through the master. The master takes it, figures out, OK, these are the worker nodes in this version. I'll touch into what's coming up next in this version, and then they flow over to the worker nodes. The metadata, you can actually replicate that metadata. When you replicate the PG shard metadata, any node becomes the master node. You can route through there. The challenge there is when you have failures, you need to make sure that the 2 metadata nodes, or like 5 or 10 that you have, are in sync. For multi-shard selects, going over to here, these get engaged when you don't have a partition key. And the logic in here is different in that PG shard pushes down the filters and the projections down to the worker nodes, pulls the data, remaining data to the master node, and then does a final pass. So that's where it applies the aggregates, the group by operations, the window functions. CitusDB is different in that if you have complex select queries and if you want them to be fully parallelized, if you want to have full distributed querying logic, and if you want to push those computations down to the worker nodes, that's CitusDB's bread and butter. So when a query comes in, a complex select query comes in, CitusDB transforms it into a form that's distributedly computable. And then you can take your PG shard, compile and build against PostgreSQL 9.4 or 9.3, and if you feel you need this functionality, you can upgrade your PG shard master node to a CitusDB master node. So you get that they are compatible that way. PG shard 1.0 is out there. PG shard 1.1 is coming up in 2 weeks. We have PG shard on GitHub, so you can look at what's been checked in from 1.0 to 1.1. Some of the features that have been checked in are shard repair UDF, seamless integration with CitusDB, copy support, select optimizations. Previously, we didn't push down the projections. Now we do, and bug fixes. Thanks to Josh for reporting some of those bugs. And then PG shard 1.2 will have more real-time analytic functionality built into it. And the reason we're here presenting is that we're looking for your feedback. If there is 1 or 2 things that are very important to you for PG shard, particularly for the upcoming 1.2 release, please do get in touch with us. We have our users list, mailing list, and we're looking for your feedback. So you're like top 2 asks from PG shard. Did you have a question?
I just had a question. Are you taking a question?
Yeah, sure.
So what happens, can you talk a little bit in detail about what happens, let's say, if I want to double the number of shards from 16 to 32? How much rebalancing will be happening?
So ideally, you'd want to pick a large enough number that, say, if you have 16 CPU cores in your cluster, you start with 64 shards or 128 shards. That way, when you add more machines into your cluster, you can easily dynamically rebalance. Of course, if you picked a small, say you started with 1,000, and then your cluster scaled out to the extent that you have more than 1,000 shards in the cluster, then you'll need to split those shards and have the hash tokens be split between the 2 shards too. That functionality isn't yet built into PG shard.
Have you considered using consistent hashing or something? The amount of rebalancing you'd have to do when you do it would be...
With consistent sharding, you still need to, when you split a shard, you still need to rebalance them. When you split a shard, half of the keys still go to one shard and the other half still goes to another shard. And then we're using the benefit that we're getting from hash token ranges gives us the benefit of consistent hashing in terms of being able to rebalance them. Because even with consistent shard, if you consistent hashing, say you have 1,000 shards and you want to have 2,000, you'll still need to have you'll still need to split that space into 2.
So are the ranges exhaustive in the sense that they, let's say I create 16 shards.
Mm-hmm.
So the 16 shards share the minus 2 billion to 2 billion.
Mm-hmm.
I see.
Yeah.
But
So
they're also exclusive.
yes, so that they don't overlap with each other. And then we'd advise that you start with a large enough number when you're initializing your cluster, so your cluster can grow into it over time.
But I mean, sometimes you don't know. Right?
Yes. And the way to do that would be to split that shard and then the hash token range for the shard. Say if it's from minus 2 billion to minus 1.9 billion. When you split the shard into 2, it would be minus 2 to minus 1.95 billion, minus 1.95 to minus 1.9 billion. So the 2 shards would have separate pieces of the hash token range. Here's the summary. PG shard is the sharding and scaling out extension for PostgreSQL. In fact, if you just want to shard your PostgreSQL instances, but don't use the scaling out part, you're more than free and welcome to do so. So you can actually use that. It does 2 things for you. It does the sharding. It provides you a sharding library and a scaling out library. To do dynamic scaling out of the cluster as you add new machines into the cluster and easily handle failures, PG shard uses many small logical shards. To be fully cooperative with PostgreSQL and to give you the usability of PostgreSQL, PG shard uses standard PostgreSQL hooks. It's simple. You create your extension, you create your table, you call a UDF to distribute your table, and then you start doing your inserts and updates. And then the last item is the one that we're really excited about. When you use PG shard along with JSONB, it makes PostgreSQL the most interesting NoSQL database. here's contact information for some of the lead developers on the project. If you have any questions, again, please do get in touch with us. We have our users list in here. And that's really all I had. Any questions?
You did mention about that parallelizing the query.
Mm-hmm.
Can you go back and explain us?
In CitusDB?
Yeah.
I could explain it.
So how is it different from what we do in PG pool?
It's different in this sense. So when a query comes in, you want to do multiple things with that query to fully transform it. First, you want to figure out pick the best join order. Like essentially, let's say I have 7 tables. What's the best join order in them? Now you want to do logical planning. So you want to create a distributed relational plan, essentially, and now you want to optimize that logical plan so you minimize the network I/O. And that distributed logical plan, you look into the commutative and associative and distributive properties of the plan that you've created so that you can push your network transfer operations as far up in the query plan as possible. So you do your logical planning and logical optimization, and then you map the logical plan into the physical execution primitives. So these could be SQL queries, these could be map operations, these could be reduce operations, or these could be collect operations. And then you execute that plan. You may, in CitusDB, we have 2 executors, one for queries that actually take a short period of time, and another for like longer running queries. So you execute that plan in your distributed cluster. So it does basically everything it needs to do to minimize the network I/O, and then so that your queries are fully parallelized, and then they operate like in real time. Does that answer your question? Before I take on another question, I'll do a mini demo because Josh told us, hey guys, this is a Postgres conference, so you need to show something with Postgres. And then, okay, let's see here if I can. Okay, I think I have it here. Okay, this is a $1 billion retailer. And then what they're doing is they have this truck delivery fleet. So they have trucks that deliver goods. And then these trucks have GPSs within them. So they're attached with GPSs. And then they report back the location of the truck, the speed, bunch of statistics essentially back to a system. This data is huge, and then it's one of the bigger cost items for this retailer. So I think their cost for just deliveries is like in the billions. And then we used PostgreSQL because previously they had this data. It was like a lot of data. They weren't making use of it. And now we mapped that. This is in CitusDB. The data gets put in 1 minute in batches with PG shard. It could even be real time. And the idea is this is all data stored in PostgreSQL. And then they want to see which places within the highways, wherever it's congested. So they want to take a look at it in a heat map so that they can figure out, OK, let's put a data warehouse here. Let's put a data warehouse there. And when we did this demo to them, I think this is going over time ranges, and then you can scroll in. The other side, the business side, was like, he looked at it and is like, man, with this old data, this is what I've been dreaming for years. Like, I didn't know I could leverage this data, like get all of it, put it into the system, and then look at it in real time, more or less. And then he actually took it a step further, said, can I actually put a data warehouse here and see what the trucks would do? And we're like, no, this is like, that's like far out there. But the idea is in this example, you can collect all this GPS data with PostgreSQL and CitusDB, analyze that data in real time over vast data sets. So that's the Postgres demo that Josh asked for. I think we're out of time. So I'll take questions here after because I don't want to hold you up. But I'm here.